where we have the query processing where the data is not available on the local nodes, has to be loaded from other nodes. And the goal is that to avoid communication as much as possible. So we have the transaction management and the query post and the transaction management. The data not available on the local node has to be loaded from other nodes. And the goal of this query processing is to reduce this kind of communication where it takes just much time. And the query processing in the distributed database management system is trying to answer a query at a site where the query is right, and if not possible, query the information from other sites, which is slow, and design the database system to reduce it as much as possible. So the most expensive part is at the join. Okay, so how to compute a join at a site B, where we want to we want to do R natural joins S, and the obvious approach is that the site B asks the site A to send R back, and then we compute this R natural join S. Better is that what if we can only send the data that is actually required? Therefore, we need the natural semi-join, where I only get the values, where we only get the matching values or have the same attributes from the database A, and we get them. We use the semi-join to get the attributes of the tuples from A, where have the same attribute, and then we send only these common attributes to S. Therefore, we can do the R semi-join S is to R times the common attributes in R and S. So where A stores R, I only got the common attributes with S from R. Therefore, it is therefore I only send this. The intuition is that the set of all tuples in R that joined with at least one tuple is the S. Therefore, I just semi-join. And what if I call projection some S, and I semi-join with S, and I store it with the S. And with the semi-join, the B sends the S prime with the common attributes from R and S to A, and the site A sends R prime, where it's the semi-join from R with S to site B, and the B sends the output R prime natural join S. And the communication cost is actually the size of the tuple in S, S prime times the size of tuple in S plus the number of tuples in R times the size of tuple in R prime. So the efficiency, it is more efficient than computing the natural in the obvious approach way, where it's like exchanging relationship. It depends, is the projection much smaller than the full relationship? Many duplicates may be eliminated. That's lost to say that do many tuples of S share the value of the common attributes? Not in this case of one of the joins is the key. Do the columns that columns are projected out require much space? And is the size of semi-join much smaller? And in general, should be the common attributes S plus the semi-join S and S would be much smaller than S. And for example, that what if we want to the film? We want the film, the semi-join with the. We want the film natural join with the city Liverpool and date equal to this in theater. In theater, we find the B in theater and films. At B, we send S prime. We project that to A, and the how does the common attributes come into play? The common attributes. and at the A it calls the semi-joint to B, and the B is called to the natural joint, and the S communication cost it might be the 20 plus 20 times 1000, which is much less than the 1000 times 1000. And then when it comes to transaction in the distributed databases, this is the chain of the data development store, that the central store determines the inventory for product at each site. More product acts between the stores to balance the inventory. The global transaction T, the global transaction T will have the local transaction T0 and the local transaction T1, T2, and T3. Therefore, the key thing is that we need to start the local transaction T0 at the central office, and T0 instruct other SAS to start the T1 to T3, and T0 determines how to move product between ties, and the T0 instructs the T1 to T2 to move product accordingly. Therefore, in order to maintain the atomicity, we can assume that to be enforced at each node locally, and it can be violated globally. Therefore, the nodes can fail during the execution of the T, and what should we avoid or wait? What about the failing node after recovery? What about the failing node after the recovery? I'm not sure what that is. And the thing is that the distributed commit. So the distributed commit, we have two, which is a two-phase commit and three-phase commit. The coordinates commit action globally, where we have select a coordinator and executed at some node decides if when and the local transaction can commit logging, and at each node locally message to send or receive from other nodes are logged too. The two phases, the phase 1 decided when to commit or abort, the phase 2 is commit or abort. Phase 1 is when to commit. Coordinator ask node if they want to commit, send the message prepare T, and they said, I see, I am prepared, so I go to a place called pre-committed. Therefore, only the coordinator allows T1 to commit. And we do not assume that the T1 can abort, something like that. Therefore, let's do it. If everything is committed, then let's say everything is committed. Okay. And if either is non-committed, no. Okay, neither is committed. And the third phase is that we can divide the phase 2 in two parts. The phase 2A is called prepare to commit, and if the coordinator fails, the other files can go to send the decision to our node, and the nodes go to prepare to. I think this one must be done first. Needs to go to pre-commit state, and then after that the coordinator can die, and so therefore we have the two phases.